Okay, it should be recording. So, hello everyone. I will share my screen and we can get started. Okay, so Javier, the stage is yours.
Yeah, so thank you everyone for joining. So this is the first session for the graph representation learning. We're mostly gonna have like two sections that we will go through. So I'm Javier. Like in general, I've been working a lot with Bayesian inference and conversational AI. Lately, I've been jumping a little bit and had to do recommendation with graphs. I'm based in Montreal. Here, there's like a album, as there's Mila. There's a lot of AI happening here. I try to host like most of the lectures, but we also need volunteers for next lecture, at least for the discussion. So I think, Peter, you can say a little bit about yourself.
Yeah, my name is Peter. I'm a PhD student in Wrocław, Poland, and I'm researching unsupervised graph representation learning. And yeah, I joined the ML Collective a few months ago, and we did some initial experimentation on representation learning for molecules. We talked about it on the last research jam, and yeah, and right now we are having this reading group here.
Yeah, so also the goal of the group, I'd say, like, is just to, this part will be like mostly for foundationals, and we join forces with Hannes, so he's also hosting a reading group where they go through papers, and he's mostly inviting some of the authors of those papers. So I think it will be much more organized. So like for now, like I see like how many people are we? We're 16. So do you guys want to go and introduce yourselves? Something about yourselves? A volunteer.
I can go first.
Kari, do you want to start?
So, yeah, hi everyone. I'm Parul. I'm a data scientist right now, and I like last year finished my PhD, which was focused on physics. I mean, the field was physics, but my PhD was focused more on network science. So I have like explored some applications kind of graph neural networks, but I haven't like gotten
Nobody.
into mathematics or research, and I'm trying to get
Somebody
into
is
it.
speaking and
I
their
think,
mic is too low.
yeah,
I think
someone is speaking.
Parul was speaking, I think.
You can go, Bert.
She is speaking currently, so I guess her mic is very low. Her voice is very low, so I couldn't hear.
Yes. Yep. Same here. My voice was too
Oh,
low.
okay. I'll try to reconnect my microphone. Can you continue, Peter, in the meantime?
Okay. So yeah, Parul, you can continue.
Oh, okay. Can you guys hear me properly now?
No, still too
Your
low.
voice
No.
very low.
Okay, is this still loud?
Not you, Xavier. It's Parul.
Okay.
Can you
I've
guys hear
actually
me?
tried to
Is it
connect.
low?
No,
It's
you
okay.
are.
Xavier, you're
fine.
fine. Xavier, you're fine. It's
Oh,
Parul
okay.
who is very low.
Okay, so whoever who wants to introduce themselves, can you guys go? So we make this a little bit more dynamic.
All right, I'll go ahead. I'm Samar. I'm a postdoc at National Institutes of Health. This is in Washington, DC. I work on protein dynamics, protein folding kind of stuff. So I'm trying to use graph representation learning for representing proteins. This is a bit more complicated than molecules, in the sense that molecules are generally much smaller in size. In protein dynamics, the representation becomes more complicated because these are way longer. And if you take the entire simulation into account, these systems are more than 100,000 atoms in size. So I'm trying to bring in graph representation learning in protein folding in some ways.
Oh, that sounds super interesting. Anybody else? Thank you, Summer.
Yeah, I can go next. So myself, Bharat, I'm currently a senior undergrad at IIT Delhi, India. And basically, I work on adversarial robustness in the graph domain. So currently, I was working on this topic from like past 8 months, and we are submitting this paper at AAAI. We are actually currently the state of the art on that. So basically, most of my work was on the related to the adversarial robustness of the graph neural network against attacks like mostly on the graph structure, like basically having perturbations of the graph edges. So I work on this mostly. So yeah.
Anybody else? Okay, Himanshu, he said. So Himanshu, as he says, I am Himanshu Didwania. Sorry if I'm not reading properly your name. Says I completed my bachelor's last year, and now I work as an ML engineer at Skit AI on conversational AI. I have some experience with graph neural networks as I work on a project to use GNNs to incorporate region semantics for indoor navigation. Excited to be part of this group and learn more about GNNs. Thank you. Anybody else?
I will go. My name is Harry, and I'm with MLC from February. Currently an undergrad at NIT Himipur, India, and just tinkering with machine learning and deep learning. So I'm not too much familiar with graph learning, but just starting out.
David, do you want to go next?
Hi, sure. Just a software engineer that is interested in deep learning, all kinds of deep learning. So hopefully this will be very interesting. Cheers.
Nishan. Or Rudra.
Yeah, hi everyone. I am actually a hardware engineer, and I do have experiences in other areas of machine learning, but I am new to this area, so hopefully I can learn, and I'm very interested in, if anybody is interested in working together on a project, I'm very open to it. Looking forward to it. Thank you.
Thank you. Shreyas.
Yeah, hello. Hello.
Yes, I can hear you.
Yeah, so I'm currently a research assistant at IIT Delhi, and I'm new to this field, and I just want to learn how it works and what I can, how I can implement it in my work.
Perfect, thank you. Also Nishan, he brought, his microphone is not working, but he says like he's a graduate, or he graduated with a master's in robotics. His experience and interest is in graphs for multi-agent and multi-robot systems and explainability. Thank you. Asil.
Hello. Hi. Yeah, that's right.
Yeah.
Yeah. So I'm a ML researcher, but I work mostly with kind of audio related stuff. And yeah, kind of don't know much about GNNs, but kind of looking forward to learning about it.
Nice. Thank you. Siddiq. Osik. Sidik. Sorry if I am pronouncing all the names incorrectly. Oh, Iwat, are you there?
Hello.
Yeah.
Yeah, this is Vaishak.
Mhm.
I'm a researcher from India. So I just finished my undergraduate where I worked on metrics completion using graph neural networks. So currently I'm working on 3D recognition and reconstruction. There also I'm trying to incorporate ideas from graph attention and transform.
Nice. I've seen like many of the latest papers that you're focusing mostly transformers now. Yeah. So let's continue with Parul.
Yeah.
I don't remember if you want.
Point transformers are very interesting.
Yeah. Parul or
Can you guys
yeah.
hear me now?
Yeah, I can hear
Yeah,
you.
it's better.
Awesome. Okay, so I'm Parul, and I finished my PhD last year in network science primarily, where I used something that I guess if you guys saw the 2 lectures where Jura Leskovich talks about traditional ML kind of stuff. I have used that in my research, but I haven't really used complex stuff. And I'm also looking forward to learning those. And well, currently I'm working as a data scientist.
Nice. And Ilya, I don't remember if you want. If anybody else is missing, just you can write if you don't have a microphone. I can read.
Yeah, I wanna go.
Oh yeah, go ahead.
Yeah, so I'm Akhil. I'm from Bangladesh. I'm in the final year of undergrad in Bangladesh University of Engineering and Technology. So I basically work on low resource NLP, particularly Hindi, Bangla languages, and I also find interest in applying graph neural nets in protein interactions and stuff like that. So that's all from me.
Do you hear me now?
I can hear you.
Okay. Hi everyone, I'm Ilya. I finished my master's in AI last year, and I'm interested in doing PhD. I'm currently working as a machine learning engineer at Hyperscience, and yeah, I'm interested in world modeling, basically trying to simulate games with neural networks. Yeah, and I'm interested in this lecture. In this meeting,
Thank you.
I guess.
Thank you. So if anyone is missing, just type or don't hesitate to speak up. So nice meeting you guys. I hope more people will join like as we continue with the course. So basically the goal will be like I see like we have people from all levels, from postdoc and undergrads. So we'll try to have like a balance between that. So it's not too bored like for the people that has more expertise. And we all can reach like to a sweet point where we all can follow the lectures. So the main goal here will be like at the beginning, just we're gonna go through the lectures. And also feel free to give like any suggestion. And as we just, this is the first time we're doing this. So if you guys have any suggestion on how we can improve, I'm happy to take it. We can continue improving. So the goal like for today, it will be like how we want to structure the reading club. So basically it will be like you guys, we want to cover 2 lectures in a weekly basis. So we meet on Saturdays at this time. And we have about 1 hour to discuss anything you couldn't understand on anything or it wasn't clear, or just to go into deep like in any topic. I see like some people have different expertise. So if you guys want to lead that discussion, I would be happy to. Do you want to add anything about the structure, Peter?
You covered the basics. So yeah, to wrap it up, we will go through the introductional parts of graph machine learning. We do that by this CS224W lectures. And at some point in time, we also want to cover what we can treat as the foundational papers in GraphML, so things like node-to-vec, deep walk, so the basic, most popular traditional methods, or like GCNs. And the Tuesday's reading group from Hannes will cover the more advanced papers. So if you want to have a look on that, then you'll need to join the other reading group. But we will focus on the fundamentals.
Yeah, and as for the papers too, I think like many of the like deep walk and many of those papers are covered as part of the course. And so it would be like up to you guys. Like if you want to go like in a specific paper, we can try to discuss. We have also different roles for each one of the, when we were presenting a paper. So we have a reviewer, an archaeologist, researcher, and practitioner, and a hacker. So like if you guys volunteer also for that, that would be awesome. So for today, at least we don't have a paper we want to discuss. We wanted just to go through logistics and the first two lectures. And also about, some people mentioned like about having some hands-on experience. We were thinking in just going through the assignments. And I think that would give us like enough experience just to play with PyTorch geometric and Network X. The first two assignments, they are already training on GNN, and basically we don't have to do anything, but we can just go through the code, and it's self-explanatory. So yeah, and on Tuesdays, don't forget, like it will be like a different time with Hannes, and they cover like more like a state-of-the-art papers. So do you guys have till now any question? And everything it should be posted on the Notion website, and we'll try to make also to update the calendar on it. Do you guys have any questions so far? And feel free to talk and just speak up. I think that would make this like more dynamic as we all talk. Yeah.
Yeah, it sounds good, like the whole outlining of it.
All right, so I think we can start with the first, just the first lecture, which was like introduction to machine learning for graphs. So this lecture was, I'd say like we have a lot of slides for the course in general, and it was like at least hard to digest some parts. Like I watched just the lectures before the meeting. So also like I think if we don't have time like to finish at some point any of the lectures, I think we can extend and just manage to cover only one lecture depending on how people feel. So yeah, and so for the first lecture we have only like is super an introductory class. So why we need like to do machine learning with graphs, why now? So basically it says like graphs, that at least for me graphs is like a universal language, and we can like the world can be represented as a graph, and it's a super powerful data structure. So we can describe so anything with relations, it can be represented as a graph. And the main the first lecture, it goes with a lot of applications. I think we can go through one of those papers at some point. It would be interesting. So and then they go like why we have a lot of types for graphs, and I think we can continue a bit. Different types, like different examples, citations, social networks, molecules, which bring like a lot of applications for graphs. But the thing is like why we need now ML on graphs. So basically we can represent relations and structures as a graph. So modeling these relationships, we can like achieve like a better performance. by using a model. So here, yeah. So we take advantage of the relational structure, and we represent things as a graph. But the thing is, like, graphs are actually hard to learn because it's not like as a traditional data set. Here we have like graphs are from arbitrary size, and we have like complex and topological structures, and there is no order, and there's like dynamical and multimodal features. It's not as working with images or text where we have like a predefined topology. Yeah, we can continue a bit. So now they say like, okay, we can go like through representation learning. So we have the common pipeline where we want to put like an input a graph and do some kind of prediction. So as in common supervised machine learning, we need features. So here, this is the whole course is about graph representation learning. So we want to somehow represent features automatically. So that's basically what we go like through some concepts of how to do that. So, and how to automatically learn these features. So basically it goes like we can map nodes to an embedding and then reuse those embeddings to do some feature, so some downstream task. And for this, we have like different tasks. And we can go from traditional methods to the most up to the latest methods like GraphSage or GCMs, starting from kernel methods. So, okay, so I think here, okay, so
basically,
yeah, go ahead.
This course, as you probably saw already in the outline, it is like divided in some parts. So today we start with introduction stuff. Then for the next time, we'll go through node and link analysis, then also some label propagation, then focus on GNNs, on the theory, and that will take most of the time. And then other applications like reasoning on knowledge graphs, subgraph mining, scaling GNNs, and applications in various fields. But we will go to that in a few weeks. And yeah, as you probably saw, so graphs are, to put it simply, nodes connected by edges, and for each different entity in a graph, you can have different types of tasks. So at the node level, at the edge level, so node pairs in terms of simple graphs. If you have hypergraphs or higher order graphs, an edge can be connected to multiple nodes, not only two, but that's something beyond the scope of this course. Then you can also look at the whole graph at once. So for example, predict a property of a molecule, or look at communities, so subgraphs. And yeah, that's basically what I just summarized. Yeah, they're impactful, as you probably know. And for example, in node level predictions, we can have proteins like somebody mentioned it previously in the introduction part that they're working on proteins. And yeah, also proteins can be represented as graphs, then we can process them to get the 3D structure. And it was done like by DeepMind with this AlphaFold, I think it was called, and released last year to show that graph processing is quite powerful to do those kind of tasks. Yeah, so the nodes are the amino acids in a protein sequence, and edges are the proximities between those amino acids. In terms of edge level processing, we can have recommender systems where we have users and items, and we need to decide whether some users will connect to certain items. And this is kind of link prediction task. So we want to predict which edges should be present in the graph. And yeah, the the basic idea here is that using not only the images, but images and the recommendations which form a graph leads to better performance. We can also use it for drug side effects, so in protein interaction networks to predict whether, for example, some drugs have an influence on some kind of proteins, and will there be an interaction between those two drugs. And in one paper, the authors showed that the predictions actually match to some evidence found in biomedical research. For subgraphs, the most known example is also by DeepMind, how to predict traffic or how to do routing. And so nodes are just road segments and edges are these road segments that are connected. And using GNNs, you can predict what are the routes and how long you will travel along a certain route. And it is actually used in Google Maps right now. In terms of graph level, you can do it for drug discovery. Again, nodes are atoms, edges are chemical bonds, and you can such represented graphs process using GNNs and then do different stuff. For example, rate whether a molecule is worth looking at, and this reduces the number of combinations dramatically so that it can really be applied in some labs, and the best looking drugs or proteins or whatever will be then synthesized, and that's just better than looking at millions or billions of molecules. We can also generate whole graphs just as another task. Also, we can use graph processing in physics simulations, for example, with fluid dynamics. So each molecule, each atom in this simulation, you can then measure the distances, for example, between those particles, construct a graph, then do some graph processing, and based on that, you can estimate the new positions of those particles and do it over and over again, and that will lead to the final simulation. So again, you have nodes, also called vertices, links, or edges, and then you can define a whole graph. And yeah, I won't go through all the details because like it was in the lecture, but you can see that you can construct graphs in various places, either like in actors in movies or social networks. Also a few examples of different networks. And now the first terminology was you can have undirected graphs where an edge is just defined as a connection between two nodes, or directed graphs where the edges are defined with a starting node and an ending node. The basic metric everyone should know is a node degree, so how many direct neighbors has a node. And you can then compute the average degree for a whole graph. In terms of directed graphs, you need to be careful because you can define 2 degrees and in degrees, so how many of my neighboring nodes are pointing to me, and an out degree, so to how many nodes edges go out of the node we consider at that time. Okay, then another thing are bipartite graphs, so graphs where you can distinguish sets of nodes which are not connected amongst them, but only between the edges are only between different kind of nodes. You can unfold these graphs to other representations, but that's not really the point here. So how you can represent a graph? basic idea is to just use a adjacency matrix, so a square matrix in the size of the number of nodes, and with zeros if there are no edges between two nodes, and ones if there is an edge. And for undirected graphs, this adjacency matrix is always symmetric, and for directed, it's not always true. Yeah, also how we can compute the node degrees, and the main
in the previous slide, L is the average node degree, right?
You mean in which slide?
For the this slide, L, it's the average node degree.
Yeah.
Why is 1/2?
It was because of the symmetry here.
Oh, but if we got like to the general formula for average node degree is 1/n. That's something I wasn't clear for me, but if anyone knows.
Oh, so I could I guess intercept here. So it's not 1/2 in the sense to take average. It's 1/2 because every edge is getting counted twice. One from the node where it's coming from, and one from the node it's going to.
Oh, okay. That this is because of the symmetry. That's why the directed is only.
That's what because of the symmetry.
Got it. Thank you.
Okay. Yeah, and the key takeaway for the adjacency matrix representation is that it is really, really sparse. So for most toy example graphs, you can always represent it like in this form, but we can take advantage of the sparseness by using other representations, just not to take up the whole memory you have in your computer, because like mostly these are zeros and there are only a few connections. And this was also shown that the average degree is something like from 1 to maybe 80 or 100 in some science collaboration networks. And the densities are like 1.5 to the times 10 to the -5th or something like that. So the adjacency matrix is basically zeros with a few exceptions for the actual edges. Other things you can do is use an edge list, and something like that you will probably see in Python Geometric, but there it is called an edge index. You can also use an adjacency list, and this is the most popular format in some libraries like Network X, for example. What else? Besides the structure, for all nodes and edges, you can also have attributes, and this can be literally anything. For example, in social networks, you can have the name of the person, the age. In recommender systems, you can have the image of the item it is representing, and so on and so forth. Yes, you can have unweighted graphs where each edge is like has the same importance. For weighted graphs, you assign for some edges some larger weights, for example, to indicate that this is more important than other ones. And you can use it directly in the adjacency matrix by putting just the values of the weight on the particular places. You can also have self-edges, so edges that go from the node to itself. You can have multi-graphs, so multiple edges between the same pair of nodes. Graphs can be connected, so like in this example, we have isolated nodes and some parts of the graph that are not reachable from other parts of the graph. Okay, if you have something like this, where you have two parts, you can divide it in a block diagonal matrix. For directed graphs, you can have strongly connected directed graphs and weakly connected. So weakly connected is when If we disregard the edge directions, then it is just connected. And for strongly, even if you don't drop the directions of the edges, it is still connected. You can have strongly connected components, so subgraphs that are connected. And that is everything. So do you have any questions for that lecture?
Yeah, so in general, like in this lecture, I think it was introductory, like why we need graphs, different applications for graphs, why now machine learning on graphs, and the different tasks that we have for node, edge, and graph level, and how to represent a graph, like the adjacency matrix, edge list, adjacency list, and how to represent different structures on graphs, like a backparking graph, a weighted graph, a self-edge graph, a multi-graph, an unweighted graph, a weighted graph, etc. So I think, guys, if you have any question here, do you would like to talk or discuss anything about this part? Otherwise, we can jump to lecture 2.
Also, if you will have any questions later on, you can always ask in the Discord channel, and then maybe either us or some other people will help you with that. Okay, so if there are no questions, then we will move to the second lecture. Okay, so this is now a lecture on traditional methods for graph machine learning. Again, it is divided in considering node level predictions, link level, and graph level predictions. Okay, and yeah, regarding, let's consider we have already some features. Then what we can do is use those features to train a traditional ML model, something like a random forest, a logistic regression, SBM, or just a neural network, and pass those features through, then train it with the appropriate labels, and that will be it. Okay. Yeah, the slides were assuming that the graphs are undirected. So that is just one assumption, but everything can be generalized to other kinds of graphs. Okay, yeah, the goal is to make predictions for a set of objects. We have the dimensional vectors, we have nodes, edges, or just graphs, and we will define the tasks. Okay, so for node classification, in most cases, we refer to this task as semi-supervised node classification. So we have a graph where some nodes are already labeled and some of them are not. So like it is represented with these gray dots here. And we want to train our algorithm on the labeled part, incorporating the whole structure, and then predict for the other nodes. Like here, the rule was something like that red nodes have a degree of 1, and the green nodes have a larger degree. Okay, and for node features, the basic ones, the traditional ones, we can define something like the node degree, node centrality measures, clustering coefficient, and graphlets. Okay, and the node degree, we already said what it is. It's number of direct neighboring nodes. But the problem is that all nodes are treated equally. So node centrality wants to capture the importance of nodes in a graph. And most popular centralities are eigenvector centrality, betweenness, closeness, among many others. And for the eigenvector centrality, we want to define this centrality value as a normalized value over the neighbors of a node. And if we rewrite that in matrix form, we can see it looks something like that, but that is just the formulation of an eigenvalue or eigenvector right there. And yeah, so what we use is the eigenvector Cmax, so for the largest eigenvalue. For the betweenness, we want to look at the shortest paths between all pairs of nodes. So for a given node V, we say it's the number of shortest paths between any two nodes in that graph that contain this particular node, divided by the number of shortest paths between any two nodes. For the closeness is the reciprocal of the sum over the shortest paths lengths between any two nodes, between the node we are considering and any other node. Sorry, it should be like that. Clustering coefficient, so it's about counting triangles, which is also explained like here, that if we consider a node and the ego graph, so all direct neighbors of that node and edges between those, then we can just count the number of triangles in that ego network, and ta-da, this is the clustering coefficient. And the generalization of such scheme is called graphlets, so where we have pre-specified subgraphs that we look into. And for example, a two-node graphlet is just the two connected nodes, there is no other. For three-node graphlets, we have either a triangle or just a path of length 3, and so on and so forth. Like the bigger the node graphlets are, the more combinations are there. This is also a problem that was addressed a bit later, that it grows exponentially, and it's in practical applications, it's quite hard to apply that. Okay. So yeah, we can then count how many different graphlets we have for a particular node and build a vector out of that and use it then as the feature vector for that node. And yeah, counting, for example, these 2 up to 5 node graphlets, we have then 73 different values to count. So we can then use a vector of size 73 to represent a node. Okay. Yeah, so to summarize it, for nodes, we can have importance-based features. So either assigning an equal importance to all nodes, we have node degree, or when we want to measure the importance directly, we have centrality measures. And for structural based features, we have also the node degree, the clustering coefficient, and all kinds of graphlets. Okay, that's again summary. Okay, next on is so predicting links or link level predictions. So yeah, we can either see a network as incomplete. So we just say, okay, we have a graph, but we assume that some links are missing and we want to predict which ones are missing. Or we can do it in a time-based scenario where we consider a dynamic graph or a temporal graph where the structure of the graph evolves over time. And for a, let's say, point in time t0, we say, okay, this is the graph and what edges will appear after that point in time. So how will it evolve? And what we do, we compute a score for a given node pair, and then for all different pairs we can generate, we just take the scores, sort them, and use the ones with the highest scores and treat them as the new links. Okay, so we can have distance-based features, local neighborhood overlap, and global neighborhood overlap. And yeah, we can, for the simplest case, we can look at the shortest path distances between nodes. We can also look at the neighborhoods, so the local neighborhoods, where we can look for two given nodes, B1 and B2, we look at the neighbors of that nodes, and the simplest example is called common neighbors. So as the name suggests, we just take this set of neighbors of B1, B2, and then compute the intersection and look how many common neighbors are there. But for nodes with a higher degree, these values can be significantly larger. So this is also a kind of bias in this kind of definition. So what we can do is just normalize it. And for example, Jacquard's coefficient does it by normalizing over the sum of these two sets, of the size of this resulting set. Adamic Adar, you just go over all the common neighbors and look at the degrees and take the reciprocal of the log of the degree. Yeah, this local neighborhood is always problematic because you can have nodes where that do not have any common neighbors, and then the values will be always 0. So we can look at global neighborhood overlapping. And for example, the CATS index is an example of global neighborhood overlap. Yeah, so the next part is about how to compute the number of paths between two nodes of a certain length. And you can easily show that it is just taking the adjacency matrix to the kth power to get a path of length k. And yeah, it was like there was a simple, let's say, proof why it works. Okay, so in the CATS index, you want to count the number of all paths of lengths 1, 2, 3 up to infinity. And how you can do that? Yeah, so that's basically the definition. So you sum the number of paths, so the adjacency matrix to the nth power, and using a discount factor for larger values. It's like here called beta. And yeah, you could say, okay, you need to sum to infinity. That's impossible, but actually, as this is a kind of geometric series, you can have a closed form solution for that. So the CATS index is computed as the identity matrix minus beta times the adjacency matrix. Then you take it to the, you compute the inverse matrix of that, and then subtract again the identity matrix. Okay, so to summarize, the distance-based features were just the shortest paths computed between two nodes. For local neighborhood overlap, you have some basic ideas like common neighbors, Jacquard coefficient, and so on, but you need to be aware that it can yield sometimes values of 0 if there are no common neighbors. And for global ones, you have the CATS index, which just counts number of paths of all lengths between two nodes. And the last part are graph level features and graph kernels, but I will pass that to Javier.
Yeah, so this is basically the whole part that we're doing machine, the old school. So now which features can we represent for graphs? So basically here also like we have kernel methods, which is just basically a function that just tries to get like some similarity. I'm going to continue. So to do that, there are two things. Like we have like a graph kernel and a WL kernel. That basically they both measure similarity. On one side there is the graph kernel that basically we can just represent a graph as a bag of words and just apply a function and to see to have this similarity. And on the other side we have the WL kernel, which basically just counts graphs and it just works as colors. Which is much better, like in terms of like it can detect different structures of a graph if there are different edges, which is what we would expect like from an actually similarity measure. You can continue again. Yeah, so it's just how we extract graphlets. Yeah, so this is basically how we compute that's basically the kernel, how we compute the kernel for a graphlet. How WL kernel works is basically just using the idea of the WL test to refine and extract features. And everything works by counting mostly. I think we can continue. Yeah. So yeah, I think so. Basically, for graphs, we have two things. It's mostly kernel methods, and we have the Graphlet kernel and WL kernel. While one is used as a bag of words that it cannot detect like some edges and some similarities, and the WL kernel fix that. And I also like, I found like now it makes sense for me. Can you open just here, like maybe you know a little bit Parul, you said that you work in the old school. Can you open this paper for a moment, Peter? I sent it in the chat.
Yeah, just a second.
Now, like many, like while I was reading this paper, I was like, oh, like diff pool. Can you go to page number 7 where for the results? I remember this paper, basically they proposed like a diff pool layer where you learn like an assignment for a cluster and a not assignment for a cluster. And basically you do this iteratively. So you have like a hierarchy to do like a readout. And at the end, just have like a not embedding for a graph embedding, sorry. And in this paper, they compare like with kernel methods. So here you have like the WL kernel and the Graphlet kernel, which for me at the time, like WLOA, it was super similar like for the diff pool that they propose. Like you see it's like super similar, like 60, 70s, like 40. And in some sense, I'd say like the 80 for Collab is like even much more consistent. So I don't know, like any of you guys know, like how hard is it to train this? Because these ones, like kernel methods, these ones are all the school. So how hard is it to train like these methods? Does anybody have any idea?
So I haven't really tried kernel methods, but I know that for the node level features and the link level features, it's fairly easy to do them using the networkx package in Python. So maybe kernel methods also have some, but I'm not sure.
Yeah, I think it should be the same for kernel methods. I was surprised like and this diff pool I think uses even more memory. Because you have to have like a different network for each one of the hierarchies. So yeah. Okay, so that was just my question. Do you guys have any question about the lecture 2, about the format, like any suggestion, how we can like discuss?
In the meantime, also, if you have any papers you would like to discuss, also you can send it either in the Discord server or through the Notion. There's also a link for that. And we can then organize for the upcoming weeks and go through these papers.
Yeah, and as for next week, we can split also like the lectures in different sections. So somebody can take control or can talk about just a section. So I think
I think we added like a form too in the Notion.
Hi, yeah. So I like the format of going through the lectures, and maybe as kind of we cover topics like papers will naturally kind of connect to, and then maybe we can kind of take some side steps to cover the papers and then resume the lectures. I don't know what you guys think about it, or
Yeah,
Yeah,
sounds
that's
fine. Mhm.
yeah. Yeah, I think that will be much better since I expect like most of us like we already saw the lectures, and if we have like anything to talk about the lecture, that would be much better. So we have like a kind of discussion instead. So we can cover a paper instead. Like as for the first week, we didn't have like any paper, so we wanted just to go through the format. But as we continue with the class, I think we'll have like any more papers to cover, or somebody will be like interested like, about a certain topic or application. So we can just present that and just have like more of a discussion of the class. So yeah, anybody else? Think we're past 2 minutes. If not, we can just wrap up there, and I'll put it in Discord like the different topics for next week. We guys can anybody can take leadership to discuss any topic, and we can like. And also, if you have any paper that you want to talk about, we can just discuss next week. Since next week we'll start with node embeddings and leak analysis.
Sounds good.
All right. So anybody else has anything to add, or?
One thing, the paper that you mentioned in chat, was it presented in the ICLR 2020?
I think it was 2018, I think.
Okay.
All right. So I think then we can. Oh wait, there is some messages. Is there any course that more focused traditional graph algorithms and networks? I don't know about that, but yeah, I think there is one course from. I'll search and post it in Discord channel. Okay.
Also, a remark is that Network X is quite popular as a graph processing library, but when working with real-world applications, you'll see that it is really, really slow. So there are some alternatives to that, and yeah, Network X is good for smaller graphs and toy examples, I would say.
So what are you using for large graphs instead of Network X?
You could use GraphTool. It's one of the popular choices, and it's really, really fast. Another thing is Scikit Network, but I didn't use it privately. I only saw it in some places used, but I have no personal experience.
Okay, thanks.
All right, so I think we can wrap it up there. Thank you guys all for joining.
Cheers, guys.
Thank you, guys.
Yeah. Thank you, and see you
Bye,
next
everyone.
Saturday. Bye.